Greetings to Mr. Anand. The topic that I have chosen is anticonvulsant, also known as anti-epileptic. The main focus of my video will be on the structure-activity relationship (SAR) of one of the classes of the drug, a drug synthesis pathway, and its metabolite. Before that, I would like to briefly explain the disease related to the use of anticonvulsants. First of all, in the human brain, glutamate is responsible for the excitatory neuronal signaling, whereas GABA is the main inhibitory neurotransmitter. When dysregulation of these neurotransmitters occur, excessive excitation of the neurons can cause seizures. A seizure is the event and epilepsy is the disorder. The main purpose of taking anticonvulsants is to stabilize the electrical activity in the brain, preventing the excessive and abnormal firing of neurons. There are almost 14 classes of anticonvulsants available in the market, some of which possess the same mechanism of action while others act differently, such as through GABA agonism, sodium channel blockage, GABA reuptake inhibition, carbonic anhydrase inhibition, and so on. Now, without further ado, I will explain the SAR of one of these classes, which is benzodiazepines, and the drug I have chosen is diazepam. Benzodiazepines consist of a benzene ring fused with a diazepine ring, which refers to a 7-membered ring containing 2 nitrogen atoms. Both of these rings are crucial for the activity of benzodiazepines, and modification at each position of the ring can significantly alter its activity, either increasing, decreasing, or abolishing it. First of all, substitution at position 1 of the benzodiazepine structure is not essential for the activity. For example, oxazepam has only a hydrogen atom at position 1 and still retain its pharmacologic effects. However, a small alkyl group substituent at position 1 can enhance the effects and is sufficient for optimal activity, as seen with the methyl group in diazepam and temazepam. Conversely, a bulky group at position 1, as seen in clozapam, does not confer any additional pharmacologic advantages and has similar properties to diazepam. The primary difference is that a bulky group at position 1 results in a slower onset of action and a longer duration of action compared to a small alkyl group, likely due to delayed bond cleavage. Therefore, when comparing the onset of action, oxazepam will have the fastest onset, followed by temazepam and diazepam, with clozapam having the slowest onset among these examples. In terms of duration of action, clozapam will have the longest duration. Next, all active benzodiazepines have a keto group at position 2, which is essential for the activity. Benzodiazepines with keto group at position 2 are known as 2-keto benzodiazepines, while those with an amino group at position 2 are known as 2-amino benzodiazepines. Diazepam, oxazepam, and clozapam, for example, all have a keto group at position 2. In contrast, chlordiazepoxide has an amino group at this position and is inactive in its original form. However, chlordiazepoxide undergoes oxidative deamination in the liver to form diazepam, which has a keto group at position 2, thereby becoming an active benzodiazepine. This conversion highlights the importance of the keto group at position 2 for benzodiazepine activity. Chlordiazepoxide has an unusually long-lasting effect, partly due to the absence of amide bond, which delays bond cleavage. Additionally, chlordiazepoxide is associated with severe side effects, leading to its replacement by benzodiazepines with more favorable pharmacokinetics, half-life, and better tolerability. At position 3 of the benzodiazepine structure, the presence of a polar functional group increases the drug's polarity, which enhances excretion and decreases the duration of action. Benzodiazepines with a polar group at position 3, such as lorazepam and oxazepam, can undergo direct conjugation and excreted directly without the needs for phase 1 metabolism. Consequently, these drugs typically have a shorter duration of action. Additionally, the increased polarity of these compounds results in a slower absorption compared to lipophilic benzodiazepines, leading to a slower onset of action. In contrast, benzodiazepines without a polar group at position 3 must undergo both phase 1 and phase 2 metabolism before excretion. This extended metabolic process often results in a longer duration of action. And due to their lipophilicity, these drugs are absorbed more quickly, leading to a faster onset of action compared to a polar compound. Moreover, the unsaturation at positions 4 and 5 is essential for benzodiazepine activity. If the double bond between these positions is removed, the activity will be reduced or abolished. Similarly, if the double bond is shifted to another position, such as between position 3 and 4, the activity will also be reduced or abolished. Furthermore, the phenyl ring at position 5 is essential for benzodiazepine activity. Substitution at the ortho positions of the ring, such as monoortho or diortho substitution with electron withdrawing groups, such as chlorine atoms, can further increase the activity. However, substitution at the para position of the phenyl ring decreases or diminishes the activity. These examples in the figure display benzodiazepine with an electron withdrawing group at position 2'. When compared to diazepam, both clonazepam and flurazepam show greater potency due to this reason. Besides that, position 6, 8, and 9 should remain unsubstituted for benzodiazepine activity. On top of that, an electron withdrawing group at position 7 is essential for benzodiazepine activity. The most commonly observed electron withdrawing group is halogen, such as chlorine. However, in some benzodiazepine, other electron withdrawing groups, such as nitro group, are also observed, as seen with nitrazepam. Among halogens, those with higher electronegativity exhibit greater potency, and benzodiazepine with stronger electron withdrawing group generally show increased potency. The examples here show that clonazepam has a greater potency than nitrazepam. Both of these benzodiazepines possess the same electron withdrawing group at position 7. However, clonazepam has an additional electron withdrawing group at position 2'. Nitrazepam, on the other hand, has a stronger electron withdrawing group at position 7 compared to diazepam, which explains why it is more potent than diazepam. Last but not the least, fused benzodiazepines like triazolam, alprazolam, and midazolam interact with GABA receptors through triazole or imidazole ring. Triazolam, alprazolam, and midazolam are benzodiazepines known for their faster onset of action compared to diazepam, primarily due to their higher lipid solubility and unique ring structures. These drugs contain additional triazole or imidazole rings which enhance their binding affinity to the GABA-A receptor complex, allowing them to exert their effects more rapidly. Also, the higher lipid solubility of triazolam, alprazolam, and midazolam facilitates quicker closing of the blood-brain barrier, resulting in faster central nervous system penetration. These factors collectively explain why the fused ring benzodiazepines achieve a faster onset of action than diazepam, despite theoretical predictions that the bulky ring structure and the absence of an amide bond might delay their effects. Additionally, the fused ring benzodiazepine produce active metabolites but in low concentration and are inactivated rapidly, thus not significantly contributing to their pharmacologic activity. This explains why diazepam has a longer duration of action because it produces active metabolites, such as non-diazepam, which have a long half-life and extend its pharmacologic effects. Next, we will move on to the synthesis pathway of diazepam. Diazepam can be prepared through various synthesis pathways. One method involves reacting 4-chloroaniline with benzoic chloride in the presence of zinc chloride, leading to a Friedel-Crafts acylation to form 2-amino 5-chlorobenzophenone. This intermediate then undergoes another acylation process when reacted with chloroacetyl chloride to form a second intermediate. When this second intermediate is treated with ammonia, cyclization occurs, resulting in the formation of no-diazepam. Finally, no-diazepam reacts with methyl iodide using dimethylformamide DNF as the solvent, leading to the methylation of no-diazepam to form diazepam. The last part is the metabolites of diazepam. Diazepam is metabolized by liver cytochrome P450 enzymes into 3 primary active metabolites that are N-bismethyldiazepam, also known as non-diazepam, oxazepam, and temazepam. These metabolites are subsequently conjugated and are predominantly excreted in the urine as glucuronides. As I have mentioned in the previous slide, diazepam does not have a polar functional group at position 3 and is lipophilic in nature, so it is required to undergo phase 1 and phase 2 metabolism. In phase 1 metabolism, diazepam is converted to non-diazepam, which is an active metabolite through the N-demethylation process, and it also undergoes hydroxylation to form another active metabolite, temazepam. Non-diazepam can be further hydroxylated to form oxazepam, also an active metabolite. Diazepam can undergo glucuronidation directly without first converting to oxazepam due to its polar nature. The metabolites of diazepam, such as non-diazepam, have a long half-life and contribute significantly to the therapeutic effects and sedative properties of diazepam. Also, both temazepam and oxazepam retain pharmacological activity similar to diazepam, contributing to its overall effects. Oxazepam in particular is used as an anxiolytic and is excreted more rapidly. Lastly, the hydroxylated metabolites undergo conjugation reactions, primarily glucuronidation. The uridine diphosphate glucuronosyl transferases are a family of enzymes that catalyze the covalent addition of glucuronic acid to a wide range of lipophilic chemicals that makes them more water soluble. Then the conjugated metabolites are excreted through the urine. That's all from me. Thank you.